Hello and welcome to Distributed Systems, as presented by me, Rahul Hegde, and the rest of Group 1, Alden Lipiarski, Shaun Goda, Daniel Lee, and Abid Azad. So what is a distributed system? A distributed system is a collection of independent computers that appears to its users as a single coherent system. It's a series of computers that distribute certain tasks. Contrary to a centralized system, which is one computer, distributed systems can solve larger, more difficult problems. They don't have to wait for a central server's response, and they're more reliable and scalable. However, they can be more complex to create and manage, and it can be a little bit more difficult to handle faults within the system. In a distributed system, the computers are connected to each other via communications networks, and they coordinate their activities by exchanging messages. The main advantage of a distributed system is that it can provide high availability and high scalability, as the workload can be distributed across multiple machines. This allows the system to handle a large number of users and requests. It also provides fault tolerance, as if one machine fails, the rest of the machines can continue to operate. Distributed systems are used in a wide range of applications, including cloud computing, big data processing, distributed databases, and web services. However, designing and implementing distributed systems can be challenging, as they often require careful management of network resources, data consistency, and coordination amongst the different machines. What are some examples of distributed systems, you might ask? Well, here's a couple common examples. Cell phone networks. There's multiple cell towers always working together to pass signals along multiple cellular devices to ensure that you can always communicate with friends and family as necessary. Virtual server instances, where there's multiple instances of software running at the same time in the same machine to service multiple different types of clients all together. Cloud computing platforms such as Amazon Web Services, Microsoft Azure, Google Cloud Platform, all are examples of distributed systems which provide ranges of services such as computing, storage, networking. Distributed databases, things like Apache Cassandra, Apache HBase. These are databases that are designed to store and manage high and very large volumes of data across multiple machines to provide high availability, scalability, and fault tolerance. Peer-to-peer networks. Peer-to-peer networks such as BitTorrent and Bitcoin are examples of distributed systems. In these networks, each node is both a client and a server. They can communicate directly with other peers to share files and transactions. Content delivery networks, otherwise known as CDNs, like Akamai and Cloudflare. These are examples of distributed systems as well, because they cache content on their servers distributed across the globe to improve performance and reliability of web applications and services. Distributed messaging systems, such as Apache Kafka and RabbitMQ. These are examples of distributed systems because they allow applications to send and receive messages between different machines with high throughput, scalability, and fault tolerance. Give me some key characteristics that are easy to understand. Well, distributed systems are scalable. They're concurrent, which means they can have multiple instances running at the same time. They're very highly available, which means there'll be a very small amount of time where you won't be able to access their services, which means, like, for example, services would be up for 99.999% of the time. There's transparency and heterogeneity, which essentially means that there is a smooth experience of communication with servers and clients, and there is a seeming singular interface that applications can hook into, even though there is usually multiple different softwares, operating systems, and programs running in the background, all communicating with each other through standard protocols. What are some of the main principles that distributed systems use today? Well, a distributed system should be able to handle a large number of users or resources at once. It needs to be able to tolerate hardware and software failures without losing data. It needs to be able to recover quickly from those failures. It needs to be able to keep consistent data, operate at all times even if components are down, distribute processing and storage amongst all nodes, handle concurrent requests from multiple clients, and also protect against security threats. Decentralization is very necessary. Distributed systems are designed to be decentralized, meaning there's no single component or node that has complete control over the system. Instead, systems are composed of multiple independent components that work together to achieve a common goal. This is how they achieve tasks such as handling large amounts of resources and users at once. Communication is also key. It's a fundamental principle of distributed systems, where they use standard protocols to have synchronous or asynchronous communication, such as through Hypertext Transfer Protocol, HTTP, TCP/IP, which is a very famous, reliable transport protocol, and REST, Representational State Transfer. Consistency is also key. It is a key principle of distributed systems because it ensures that all components have a consistent view of the system state. If the views of the system state are not consistent, then that means that different users will get inconsistent results, and that is not something that we want. They could potentially get worse experiences in some parts of the world. They could get some better experiences somewhere else. We want to provide a uniform experience for all people, and that is why consistency is key. This can be achieved through mechanisms such as replication, synchronization, and consensus algorithms, which all ensure that components agree on the current state before proceeding. Fault tolerance. It's very, very important to make sure that one system can continue operating even if parts of it fail. Scalability. It's a very important principle which allows us to handle very large amounts of clients, very large concurrent requests. And security. Security is very, very important. It is an essential principle because there are many threats on the internet. Security mechanisms such as authentication, authorization, encryption, and firewalls are all used to help protect the system and its data from unauthorized access and attacks.
So when designing a distributed system, you want to make sure that you're building a resilient system. This means that even if there is a failure, it will still be able to function. Two types of errors that can occur within the distributed system are network failures and node failures. Network failures happen when one or more nodes are unable to communicate with each other. This means that packets are not guaranteed to transfer between nodes. A node failure occurs when a node becomes unavailable or unresponsive. While you can't prepare for everything, it is important to be able to handle failures based on importance. This importance can be determined by frequency and impact they have on the rest of the system. So there are several methods that can be implemented to handle a failure in the system. One method is partitioning. This is where a node will temporarily cut itself off and await a resolution. Another option is quorum. This is an algorithm that will parse updates based on the node consensus, which includes failed nodes. This prevents a confusion between partitioning and failures. A third way to handle failures is with a fail-stop behavior. This is where a failed node will restart from either the beginning or a checkpoint. Nodes that have Byzantine failures will also hold this behavior. However, this can be dangerous and could lead to cascading failures. By utilizing distributed consensus protocols, nodes will agree on what updates should be applied. Such protocols include Paxos, Rift, and Zab. This ensures system-wide updates and maintains consistency and correctness. To keep order, systems are distributed, locking, and synchronization in order to keep global order. This ensures that updates are applied in the correct order and coordinates access to shared resources, which only one node can modify a resource at a given time. This also avoids conflicts and ensures updates are consistent. Nodes in a system vote by achieving consensus, using consensus algorithms to ensure agreement on a proposed decision. Each node is assigned a vote, and they work together to come up to a decision. Usually it is a simple majority needed, but it can vary by implementation.
Alright, so who exactly is Leslie Lamport? Well, for starters, he's a computer scientist. A computer scientist that had a huge impact in the development of distributed systems, which I'm going to call DS for short. First off, he developed a way for nodes in the DS to timestamp their actions. That way, other nodes in the DS can read these timestamps and know if they're outdated. This will help the other nodes update accordingly. He also developed the Paxos algorithm, which practically grabs the general consensus from other nodes to agree on one update, even with the event of failed nodes. This would send the update to the rest of the DS nodes. And he also founded reasonings behind existing distributed algorithms to aid in the development of a DS. To sum it up simply, he helped in the development of how updates are managed in a DS and stay consistent. One other thing, he developed Byzantine fault tolerance. I'll explain what a Byzantine fault is shortly, but this practically handles the event of a node failure or attack in a DS. He's done a tremendous amount of work towards the distributed systems we use today. Now, what exactly is a Byzantine fault? It's pretty much the event where a node receives mixed signals. The diagram on the right actually explains this. The node, Lieutenant 1, is receiving orders to both attack and retreat. Well, obviously he can't do both, so he might do the wrong action instead of the one he was supposed to by his commander, a miscalculation. He might do something else that doesn't really help his squad system, being redundant. Heck, he might just do nothing at all, just shutting down entirely. That's what may happen to a node in a DS when it receives the signal. It could be redundant, perform the wrong calculations, or even just shut down. So how do we account for this? Well, Lamport earlier actually gave us a solution. In the case of such an event, we can use many algorithms, including Paxos, to avoid sending updates from the troubled node to others. Before we ship out any other updates to any other nodes, let's make sure that the nodes trying to send us certain updates are in agreement. We could also have nodes sign off on their messages before sending, as per the design of a practical Byzantine fault tolerance design. Using a digital signature for authorizations, we can have the nodes that receive a message authenticated, making sure it's coming from the right node or a person, say the lieutenant expecting his orders from the commander only. With this, a DS becomes more reliable in the handling of its data among its nodes. Let's shift gears a bit. In the real world, us computer engineers are developing a DS for a client. How exactly does a client rate a DS so that they know what they're paying for is of quality? Well, they measure it based on its reliability and performance. Using a service level indicator, they measure how long the DS can run and how fast it performs operations. From this SLI comes a service level objective. Obviously, clients want their existing DS to be better. So in order to do so, they set down goals for those working on the system to improve the SLI. These goals can prove to lead to a much more efficient DS. But suppose some of these engineers don't deliver on these goals. Maybe they have something more on their plate or whatnot. Well, the clients typically would have these people they hired working on the system to sign off on a service level agreement. This is practically a written contract where the engineers working on the system promises to deliver on the SLOs placed. Otherwise, they might face some consequence. Although sounding a bit menacing, it does help build trust between a client and an industry.
In this slide, we will be discussing various types of software architectures that are commonly used in modern software development. As you can see on this slide, we have listed 5 different architectures: client-server, peer-to-peer, 3-tier, microservices, and publish-subscribe. First up, we have the client-server architecture. This architecture is based on the concept of a client, which is typically a user interface or application communicating with a server, which is responsible for providing the required data or services. This architecture is widely used in web application and is very effective in handling large volumes of data. Next, we have peer-to-peer architecture. In this architecture, all the nodes in the network act as both clients and servers. Each node is capable of initiating and responding to requests for resources or services, making this architecture highly decentralized and resilient. This architecture is commonly used in file sharing applications. Moving on, we have 3-tier architecture. This architecture is designed to separate the presentation layer, application logic layer, and database layer into separate tiers. This separation allows for greater scalability, ease of maintenance, and flexibility in the application. Fourth on our list is microservices architecture. This architecture is based on the concept of breaking down complex applications into smaller, independent services, each with its own functionality. This approach allows for greater flexibility, ease of deployment, and scalability of the application. Lastly, we have publish-subscribe architecture. In this architecture, publishers publish messages to topics or channels, and subscribers receive messages from those topic or channels. This architecture is commonly used in messaging systems and event-driven architectures. Next up, we will discuss the two types of software components that make up client-server architecture: clients and servers. Clients are end-user applications that request services from servers. They are usually installed on a user's device and are responsible for making requests to servers for data or other resources. Clients can be web browsers, mobile apps, or desktop applications. On the other hand, servers are back-end systems that provide services to clients. They process the requests made by clients and respond with requested data or resources. Servers can be web servers, application servers, or database servers, to name a few examples. The communication between clients and servers happen via network. In this slide, we discuss two types of network: the internet and intranet. Internet is a global network that connects multiple autonomous systems worldwide. On the other hand, the intranet is a private network within a particular organization or enterprise. Next up, let's talk about scalability. One of the main advantages of client-server architecture is its ability to scale with ease. As the number of clients increases, servers can be added or upgraded to handle the increased demand. This means that the system can accommodate growth and expansion, allowing for more users to access it without compromising on its performance or speed. Next, we have security. With client-server architecture, it is easier to enforce security policies and protect sensitive data from unauthorized access. By having a centralized server, you can control who has access to the system and data. This helps to prevent security breaches, data leaks, and other malicious attacks that could harm the system and its users. Thirdly, we have centralized data management. This is also another key benefit of client-server architecture. By having all data stored and managed on a central server, it is easier to maintain data consistency and integrity. This means that all clients have access to the same data, which reduces the chance of data inconsistencies or errors. Lastly, we have flexibility. With client-server architecture, it is easy to integrate new clients or services without affecting the underlying system. This means that you can add new features or functionality to the system without having to change the entire system's architecture. This helps to reduce downtime and minimize disruption to users. What are some disadvantages of the client-server architecture? The first major disadvantage is the high cost. Client-server architectures require specialized hardware and software, which can be quite expensive to set up and maintain. This can be a significant barrier to entry for smaller organizations. Secondly, client-server architecture is heavily reliant on a network for communication. This means that response time can be slower and downtime can occur if the network fails. This can be especially problematic in high-pressure environments where quick access to data is essential. Thirdly, client-server architecture is more complex than other types of architecture. It requires a higher level of technical expertise to design, implement, and maintain the system. This can be a challenge for smaller organizations that may not have the necessary resources. Next up, let's go over peer-to-peer architecture. Nodes, which are one of the key advantages of peer-to-peer architecture, is its decentralized nature, which allows for scalability and cost efficiency. Each node has equal rights and responsibilities, and nodes can join and leave the network dynamically. The network is also able to adapt to changes in the number of nodes and their location. making it a highly dynamic and versatile system. However, as with any system, there are also some disadvantages to consider. While decentralization can be an advantage, it also means that there is reduced control over the network as a whole. Additionally, the variable network performance can sometimes lead to inadequate distribution of resources or services. Overall, though, the advantages of a network of nodes outweigh the disadvantages. By leveraging the power of each individual node, a network can provide a highly scalable, cost-efficient, and flexible solution for file sharing and real-time communication. Let's dig deeper. One of the key benefits of P2P architecture is its decentralized nature. Unlike traditional client-server models, P2P architecture distributes data and resources across multiple nodes, which makes it more robust and resilient to attacks. By removing a single point of failure, it reduces the risk of downtime and ensures that the network is always available. P2P architecture is also highly scalable. Each user contributes to the network's resources and capability, which means that as more users join, the network's capability grows accordingly. This makes P2P architecture ideal for applications that require high level of scalability, such as file sharing or streaming platforms. P2P architecture can lead to significant cost savings. Traditional client-server models require a dedicated server, which can be expensive to purchase, maintain, and upgrade. In contrast, P2P architecture leverages the computing resources of individual nodes, which means that there is no need for a dedicated server. This can result in significant cost saving over long term. What are some disadvantages of P2P architecture? The first disadvantage is related to security risks. Since P2P networks don't have a centralized server to filter malicious content, they are more vulnerable to malware, viruses, and other forms of malicious software. Another disadvantage of a P2P architecture is the quality of service. P2P networks often suffer from inconsistent performance since they rely on the resource and bandwidth of individual users. This means that if some users have limited resources or slow internet connections, this can largely impact the performance of the entire network. Resources constraints are also a significant disadvantage of P2P networks. The resources available in P2P networks are limited by the resources of individual users. Since most people don't have super expensive hardware, the overall performance of P2P networks can be lower than that of centralized architectures. Lastly, P2P networks can facilitate the sharing of copyrighted or illegal content, creating legal risks for users. This is why many governments and companies monitor P2P network to prevent the spread of such content.
Alright, cloud computing. Maybe not some computer in the sky, but rather something much cooler. Think of it as a computer sending signals or messages to another computer or device and have it manage something on its own behalf. Cloud computing is the unmanned availability of computer resources such as storage or computing power and have it done all over the course of the internet, or as some might call it, the cloud. Instead of being limited to their own physical infrastructure, users can access and manage their resources online and on demand, typically managed by a third-party provider. But why is this exactly better than just using your own computer? Well, first off, it's cost efficient. There's no need to dump hundreds of dollars for an SSD, maybe to store that video presentation you're making, when instead, you can have it uploaded to the cloud and access it whenever, only paying for the resources you use. And since it's cost efficient than upgrading the physical hardware, it's also scalable. If we need more resources or maybe we need to cut down, depending on the demand, it's easily doable. And it's also accessible. Once in the cloud, you don't need to use the same computer to access that presentation you just uploaded. You can access it from any device as long as you got a stable internet connection. It's reliable as well, as providers typically make these systems highly available with several backups just in case. And finally, it's flexible, meaning we can customize the cloud computing experience to fit our needs and requirements. It does sound all amazing, but there might be some drawbacks we have to consider while utilizing this. Some of the drawbacks come mainly from having the need to send these resources over the internet. As such, that makes these resources liable to cyber attacks and data breaches, meaning there's a possibility that our data could get stolen or even lost. Plus, as said, it's accessible as long as we have a stable internet connection. If not, we can't really send our resources to, and we could even be locked out from our uploaded resources. Heck, we could also be locked out due to a service outage or even a disruption. But our clients do have limited control over their infrastructure holding their data and their used resources, meaning we can't do much under the restriction of their provider. Though the last two could be mitigated and glanced over, the danger of cyber attacks and stolen data is particularly intense. How do we exactly deal with this issue? Well, let's take a look at hybrid cloud computing. This is pretty much the combination of public cloud computing, which we discussed earlier, and private cloud computing. Private cloud computing essentially stores a user's data in a more private internal network, making them more secure. This helps deal with the issue of cyber attacks while keeping the perks of cloud computing. Let's take a look more into the benefits. As we said, hybrid has improved security due to the use of a private cloud infrastructure. Now you might be wondering, why exactly do we not just use private entirely? Well, private cloud infrastructures typically cost more to use than a public one. Instead of paying more than what we need, we can have our application choose to run on either types, depending on the needs or requirements. This proves to be more cost efficient and better for business. With all that being said and done, cloud computing is an amazing innovation that allows us to do more without being locked behind the limits of our low-end personal computers.
So distributed file systems are a type of file system that allows multiple computers to share and access files across a network. In a distributed file system, the storage resources are distributed across multiple computers, but the users and applications can access the files as if they were stored on a single system. This structure allows users to access and share files at the same time, which can increase productivity and collaboration. One advantage to using a distributed file system is that it provides fault tolerance and data redundancy. It achieves this by replicating the data across different machines and networks. Examples of distributed file systems are NFS, which is Networked File System, AFS, or Andrew File System, and HDFS, which is Hadoop Distributed File System. So this chart compares some of the most well-known distributed file systems. As you can see, there are variations in the target audience, where HDFS is intended for lots of users, which is larger than AFS, and while NFS is aimed towards smaller networks. They also differ in how they authorize users. AFS uses Kerberos authorization, while the identity is trusted by NFS, and the identity in HDFS is just what the OS tells. So a distributed database system is a type of database management system, or DBMS, that stores data on multiple computers that are connected via a network. In this type of system, the data is distributed across several physical locations rather than one central location.
Hello, this is Daniel, and I will be finishing off essentially the rest of this presentation. So first of all, we're going to go over a little bit of the distributed system designs. And before we go over those kind of things, we need to go over the CAP theorem, which states that any distributed data storing can only provide only two of the following three guarantees. And these three guarantees are consistency, availability, and partition tolerance. And just as an example, we have consistency and availability, which can be traded off in the event of partitions. With therefore, the design decision states that the system can be either consistent or available, but it cannot be both. And you can see from the diagrams on the left and the right how this CAP theorem works, where you can see two of the three being used at a time. There is no way all three can be used. Moving on to some consistency models, there are some rules for parallelism. Some of these examples do include messaging apps, GitHub, distributed file systems, and these are drawn from multiprocessor cache coherences, and all writes also are instantly visible to all subsequent reads, but it's also slow for distributed systems, and therefore it assumes that each process only cares about writes done by other processes. Each process, though, has its own private copy or cache, and is faster than strict consistency for distributed systems. And we're going to quickly move along to clock synchronization. For pairwise synchronization, we can use network time protocols, abbreviated as NTP. Or we can also use Berkeley algorithms for client-server systems. This is a time server that polls every machine and adjusts all the clocks periodically. Another synchronization method we could use is logical clocks. These are vector clocks and are a more advanced version of just normal logical clocks. But either way, each method of synchronization is that the main goal is to get the correct order of events. It doesn't matter what it does, as long as it gets that goal of keeping everything in order, keeping everything in check. As long as that's good, we are good. And with these designs, we can actually see them happen in the real world. For example, we have Rocket League. It's a game where a multiplayer game where 3 players on each team have to maneuver a soccer ball with a car and essentially play soccer. And the challenge with this game is, as for every mainstream multiplayer game, inputs need to have little to no delay within the games. So servers can't wait for a client input, or else everyone will experience a delay, and that's not very good when you want to try to win against the enemy team. So the solution to that is going to be lag compensation, which predicts an action with server confirming that the action did in fact happen. And to apply this, we're going to take a look at how Rocket League's networking works. It has server buffers that buffer essentially the player inputs, and the client, and this gets sent to the client, where the client predicts every action that is being performed. So it hasn't actually happened, but in order to reduce the amount of input delay, it tries to predict what the player is going to do, and with that, it works with the server to try to figure out what the action is and see and determine if a player did hit the soccer ball or essentially not. And this input buffer is how this works. So the client sends inputs for every physics frame. The client inputs actually don't arrive at a constant rate due to the amount of actions happening. So the server then buffers the client input, which reduces the need for a pause for any input, which is really good if you want a seamless experience in a game of Rocket League. But the downside to this is going to be that just a little bit of extra latency. So you are going to experience very small input delay. It's within like tens of milliseconds, so it's not that big of a deal, which is good in terms of the trade-off you're getting. You're getting everyone getting what they see is what you get, with in turn for a little higher latency in the game. And that will be my part, and we'll pass it over to Rahul for any closing thoughts on this project.
And that just about wraps it up for our presentation. These are some of the works that we referenced, and we viewed some videos from the Distributed Systems YouTube channel on YouTube. Thank you so much for watching. We hope you enjoyed the presentation. Are there any questions?